Um, I'm Rick Nelson. Thank you very much for being here. I have to warn you up front that my Zoom skills are not great. I'm a dinosaur. So you may have to help me a little with the Zoom, but if you're patient, I think we can have a good time this evening. I think Kristen put the note up in the chat room. If you have access to some paper, a pen, and either a tabletop or a clipboard to write on, Carrie's got it there. I'm going to ask you to do a little bit of problem solving during this workshop, and I think that'll help you. So if you need a minute or two to go off and get something to write on, that would be good. That's 2 minutes.
That I
Okay.
think might be the shortest 2 minutes ever, Rick.
My Vanawife's not too good. Up, down. Here we go. Let's go to.
Do we need our slide rules?
I wish.
I gave mine away at the last NEAC meeting.
Let me see if I can go down one now. Come on, cooperate. Okay, clipboard, tabletop, pen, and paper. If you have the paper, please copy my email address. Can you see it on the screen? Because if you have questions when this is done, I'll try to answer them. I will tell you a bullet 3. All of today's slides will be put up at a place you can find them. And I'll give you that address at the end. And Kristen's going to put up the Google Docs page.
I mistyped your email. Yes, I'll put the Google Doc in a second.
And Kristen, you might be able to look at the all the people in attendance and tell me how many people waved their hands at the screen when I ask how many of you teach college. Can you do that?
Hold on.
Wave your hands in front of your face like this. If you
I can't
teach
get
college.
everybody in at the same time.
Give me an approximate percentage.
Hold on.
College teachers.
I can't do that while I'm recording the session.
Okay.
But we could put it in the chat.
All right. I would want to know how many of you teach AP chemistry. Those of you want to wave your hand a little. I see some of those. Honors chemistry, being chemistry for people who want to take college general chemistry, maybe want to be STEM majors. Here's the question. In New England, the most people teach Chem 1 honors in grade 9, 10, or 11. Anybody have a general answer there?
11,
11?
10 in the advanced track.
Okay. But
Freshman.
really, freshman for chemistry. Okay. How many people say yes if they give an ACS high school exam or college exam at the end of their course? Just say yes.
Yes.
One yes. Okay. I'm going to ask now, if I can do this, if you've read any of these books. Has anybody read any of these books? Oh, I've got some summer homework for you. Can you see those 2 books? Has
Oh, yeah,
anybody
Daniel-
read Daniel
Yeah.
Willingham's Why Don't
Yeah.
Students Like School?
Yeah.
Okay. Some yeses. Has anybody read more than a page or 2 of this paper? Say yes.
Yes.
One. Couple?
Yes.
Okay. I'll be looking for questions from you guys and keep track of the mistakes I make. 1 or 2 people raise their hand and just say what you're interested in hoping to learn about tonight. Carrie, you go first.
Well, I just want you to recapitulate what we've worked on together. The idea of having a good math background and teaching it specifically from a chemistry standpoint. In other words, I call it chem math, which mathematics used in chemistry rather than the formal math in the math classes.
Here, Susan Erickson, what were you hoping to get out of this? I can see your name.
I
one of the things that I see a lot with my students is we'll go through a problem solving technique or algorithm and I'll walk away and I'll come back a few minutes later and I'll talk to the same student and it feels like they haven't seen it before. Like, we just talked about this, but you have no idea what I'm talking about. And as I was reading this article, I was like, oh my God, this is making so much sense now. So what I'm hoping to do is figure out a way to kind of break those, chunk it better so that they can remember stuff.
Ooh,
And
chunk
then-
it better.
and then apply it to, again, more complex problems. Also, it with the AP chemistry students, it reinforces the need for them to have some things that are automatic so that they don't have to spend time looking those up and trying to find polyatomic ions, for example, because the problems get so much more complex in AP chemistry. They need to be able to, they need to have more space to do the more complex problems. So it'll help
Okay.
me, it'll kind of help me reinforce that for them as well.
Now you're taking away my thunder, so we'll stop there. That's good. That's good to hear. Can anyone define for me, who hasn't spoken yet, retrieval practice? Somebody say yes. Okay, how about distributed
Yes.
practice? Distributed practice. Who can do distributed? Anyone? Massed practice. Anyone? Massed practice means cramming. We'll talk about that today too. We'll talk a lot about working memory down here. Can you see my cursor? I made it red. Folks, I'm obviously a dinosaur, but when I started doing chemistry education in 1969, we knew a whole bunch about the science of chemistry. And we knew hardly anything about the science of how the brain solved chemistry problems. So chemistry education was half science and half art. Over time, that's changed. Since 1995, the scientists have developed these amazing tools to watch the brain think. And in the limited areas of reading, math, and science, where problems have clear right answers, science, it turns out, can give us a lot of help in designing effective teaching. They can tell us a lot about what does work and what doesn't. Why do I say that with any confidence? I got involved with a group of college professors teaching chemistry long about 2008. I'm not that old. And we were looking for the question of how can we improve the success of students in college general chemistry? How could we lower the DFW rate, they call it, so more kids pass? And Craig is at Daniel College in Maryland. 3 years of his 2-semester general chemistry. He had a lot of scores. See the blue bars? He was actually running about the national average, which turns out to actually be about 40th percentile. So we talked about what we could do to do two things. How could we make chemistry more efficient so we could cover material quicker? How could we make it more effective? And how could we add some math help, which seemed to be where students were having the most problems? We tried that for a year. Dr. Craig gave the ACS test again. And what happened to his scores? Red bars. The red bars are a year after, or the year after he tried the experiment. His students went from the 40th percentile on the test to about the 64th. And folks, for a 1-year jump in scores on the ACS exam, that's pretty good. That gave us some confidence that the methods which we were trying the paper we collected, and this is open access for people, and I'll give the link in my resources. We collected the recent ideas that cognitive scientists are telling us about how we can teach chemistry more effectively. And I'm hoping when this is done, you'll have a chance to go back and look at the paper. It'll reinforce through the practice over time. So today we're going to relax and just talk and listen. Why do students take honors chemistry or AP chemistry or college general chemistry when they could take an easier course? Let me call on M. Hannah. Why do they take the hard course? Why do they take the hard course?
Are you talking at the high school level?
Yes, or the college, whatever you teach.
Yeah. So I think we're unique in that we have our freshmen take chemistry, and we have the two levels, an accelerated and a regular chem. And the idea is that they loop again in their junior year, and they take the two UConn classes here in Connecticut.
Okay.
And so typically they take the more challenging class so that they can earn that college credit before they're done the high school program.
So you think it's in part just to get the college credit?
Not just the college credit, but also the advanced placement piece. At UConn, it's a pretty challenging course in terms of just passing it. And then I think a lot of those folks are, so they get a little more attention, smaller class size, certainly the contact hours at the high school level. And so those are some benefits to it, to that program. And I also think that at a really young age, they're picking their possible career paths. And so I think for all those reasons, they do it. Yeah.
That's a good answer. I like that answer. I did some studies on how many people major in various things. And the NSF keeps this data on what people graduate with college majors. And what we found was that the percentage of students who actually graduate with chemistry majors, 4-year degrees in college, is less than 1%. The percentage that graduate in engineering is running up at about 4.5%. It's down from what it used to be. The percentage that graduate with a healthcare degree is up about 6 or 7%. I didn't show it because it's hard to track the nursing programs. Nursing doesn't always give a BA. They give an RN degree, and NSF doesn't know what to do with that. But we know that a whole bunch of people who take chemistry take it because it's a foundation for engineering, where you need to take both chemistry and physics, and healthcare, where you need to take both chemistry and biology. So not so many really want to be chem majors, but they want to do the interdisciplinary fields that require chemistry because that's where the jobs are. And that's where we really need people is doctors, nurses to care for old people like me, and engineers to use to build all these fancy gadgets. Those kids are smart. Some of them want to be opticians in pharmacy. Some want to do medical technology. Chemistry is a foundation for all of that. And in fact, in college, to do any of these majors, what's the first science course they usually have to pass? General chemistry. So we set as a goal to address this problem. President of Council of Advisors in Science and Technology told us of the students in 2006 who started a STEM program in college and intended to major in STEM, 41% had a STEM degree 6 years later. 60% were dropouts. Our small group decided our goal would be increase the percentage of kids who are successful, not just in chemistry, but are successful in STEM majors, where they have to pass both chemistry and physics, in most cases, to continue in the major. And I guess I would plead that if you teach chemistry, you keep this goal in mind, that we're not so much preparing chem majors, we're trying to help those kids who mostly want to major in healthcare and engineering and other science, multidisciplinary occupations. What happens in college in Gen Chem 1? SUNY Albany did a study, 1,800 kids started, 34% dropped out DFW, 1,120 started second semester Gen Chem, 36% of those were DFW. So just like with the STEM degrees in the previous slide, which maybe I can get back to, all the data we have indicates that college general chemistry has high failure rates. And we wanted to do something about those failure rates. how can we prepare kids for STEM majors? What holds kids back in STEM? Carrie and I have talked about this a lot. What we found is that kids who come in, we could teach them the chemistry up here, but we kind of had to assume that they could take these units and simplify the units to get from here down to here. And we were finding a lot of the kids could not simplify a fraction that had 1, 2, 3, 4 fraction bars. They didn't have the math background. Throw at them a square root, complex units, throw at them the Nernst equation. You know, back in the day, the older people will tell you, this math over here inside this parentheses is stuff we could all do in our heads. Because when we came up, there were no calculators. Even today, you may teach the kids how to do mental math and solve this. And it's, frankly, it's easier to solve this using mental math with a little practice than it is to try to enter all the data in a calculator. So one of the things we learned in looking at the cognitive science was the same thing. The ability of the kids to use a calculator for a complex calculation where the numbers are tough depends on their ability to solve easy calculations that might be complex, but the numbers are simple and they should be able to solve them if they know their mental math. What happened to mental math? High school, not even high school, 8th grade. What happened between 1978 and 2001 to math skills? The best data we have is from Iowa, because Iowa used the same test for 23 years. What kind of math do we use in chemistry most? Computation or non-computation? Which is it? Mostly we do computation. And starting about 1990, computation skills across America fell apart. What happened in 1990? Who wants to volunteer? 1990 is when the NCTM, the National Council of Teachers of Mathematics, told all the states in their new state standards, they ought to let kids use calculators in elementary school. And by 2003, over 30 states in the US were letting kids use calculators to do arithmetic in the 3rd grade state testing. And folks, if they were using calculators for arithmetic in 3rd grade, their mental math skills were getting rusty if they ever knew them in a hurry. And it turned out that had an impact. Virginia is my state. Same kind of results. Kids got good in math reasoning under the NCTM standards in math. Computation skills tended to fall apart. What did that do to the US math skills? In 2012, the Organization for, what can I remember? For Economic Cooperation and Development, an international group, gave a test of US numeracy skills. Top scoring nations of 22 nations were Finland and Japan and Belgium. Where's the United States? Can you see it? Give you a hint, look over here. Out of 22 nations, where was the US in math? Our adults between ages 16 and 34 were dead last. Is that visible on the screen? Okay,
Yep.
I got a little bit of a bigger screen here, I think, than you do. Gotta take down my gout. I'm gonna leave it up. Okay. Good news for those of you in New England. Watch this. This is the TEMS test in 2011. They tested number skills. The top scoring nation in number skills was Korea, South Korea. Japan was at 557. The US was way down at 514. Average of all nations was 500. So Japan had 557. A few states let their kids be tested in TIMSS. How did Massachusetts do? Who can read the number? Anybody?
Yep, it's 567.
567. How did Japan do?
557.
Kids in Massachusetts beat Japan in numeracy skills in 8th grade by 10 points on this test. Good for Massachusetts. Good for Minnesota. They tied Japan. What did Massachusetts and Minnesota do that was unique in the United States? For most of this period, they didn't let kids use calculators in elementary school. They had to know their mental math. They had to be able to do that mentally. So our project goal was, can we make more time to teach a little bit of math by making chemistry more efficient? Because we knew that the states weren't teaching a whole lot of mental math anymore, and that was hurting us. The cognitive scientists came in and gave us some help. Here's what they said. The brain stores information in neurons. Each neuron can hold a little bit. The neurons connect to each other across synapses. By trading information, you can think and solve problems. We tried applying the cognitive science findings to teaching chemistry, and we got very good results. Here's one of the questions that came up early on. And you've been faced with this. In teaching kids, do we primarily ask them to memorize facts and algorithms? Or do we tell them, don't memorize, learn critical thinking and reason? It turns out this was a big debate. Cognitive science has an answer to this question, which we're about to learn. First, we're going to do an experiment. I want you to take your blank sheet of paper. I want you to use a pencil or do this in your head. No calculator. I want you to do this calculation. Got that pencil? Are ready to do it in your head? Here we go. Solve. Wave your hand when you have the right answer. There you go. Some of us can do these in our head. Our mental math is good. The correct answer is what, folks?
7.
I hope so. Who said that? Try again.
9.
Very good.
9.
There you go. I like to see Carrie's fingers held up there, 9 fingers. Didn't mean to pick on people. Your mental math is rusty. Here's my question. Could you do it fast? Could you do it in your head? Did you reason or did you apply a well-memorized automatic algorithm? People who said they reasoned say yes. People who say they used an algorithm say yes.
Yes.
Yeah.
Yes.
I think that's the case. How does cognitive science explain what you did? Did you reason or did you remember? Cognitive science says you looked at the problem and you loaded it into working memory in your brain through your eyes. Working memory is where you solve problems, and it's the part of the brain where you think. Once it was loaded in, you noted the form of the equation, you looked over at your long-term memory. Well, what did you know about this kind of equation? Identified the problem type, remembered the steps of the algorithm that solved, and by cued retrieval of the arithmetic facts, subtracting 2 from 29, you process the data step by step really quickly to reach the problem goal. Some of you are so good at this, you did it in 3 seconds. Working memory is key here. It has many functions. It's where you think. It's temporary. You can only store information there for a little time. You know, your long-term memory has a huge amount of information you've accumulated over life. But working memory holds that small bit of information that you're thinking about at the moment. And we say that it's composed of slots that can briefly store chunks of encoded information. Working memory is also where learning begins. If you do think about a problem and get it right, long-term memory tends to store what you did. That's how the brain learns, is it decides, hey, I got that problem right. I better hold on to that. And you tend to wire together among your neurons the pieces of the problem that you used that were connected when you solve successfully. That's how learning happens. Here's the problem. Science discovered in about 1995 that working memory is very good at handling well-memorized information, but is exceptionally limited when handling information that has not been well memorized. This is why the kids who didn't know their math facts were having trouble, is because their math was no longer, they didn't know their times tables anymore. They were using calculators as a crutch. Here's what science says specifically. During problem solving, working memory can process all chunks of knowledge that can be quickly recalled from long-term memory, like 29 minus 2, plus up to 3 to 5 chunks for up to 30 seconds that you can't recall. This is like the unique problem data of the problem. Let's try another experiment. I'd like you to gather your pencil and paper again, but put down the pencil. I'm going to give you 10 seconds to memorize something. I don't want you to write it down. I want you to store it in memory. Okay? No pencil. 10 seconds. Memorize this number. I can see somebody that's smiling. Without lifting the pencil in your head, I want you to multiply that number by 100. Now I want you to divide it by 10. And now I want you to write down the result of that calculation, or as much as you can remember. Guess if you need to. Written down? Okay. Now, we're going to try this one more time. Gather your paper and pencil, 10 seconds, put down the pencil, do not write down the number. I want you to store it in memory. Ready? 10 seconds to memorize this number. Go. Without lifting the pencil in your head, multiply the number by 100, divide it by 10. Write down the results of your calculation as much as you can. Back. Back. And now check your answer. Folks, which one was a whole lot easier?
First one.
The first one, because you recognize that collection of digits as a very familiar what? Chunk of memorized data. That wasn't one number. That was a chunk of numbers that you had memorized as a bunch in chemistry. About how many of these digits could you remember? And then process just a little bit. As many? I don't think so. This is how many chunks? 1, 2, 3, 4, 5, 6, 7. They're all disconnected. How many chunks can your working memory hold? 3 to 5, scientists say. So this was one chunk. Even with some processing, you had a shot at remembering this one because it was something that you had well memorized over time. Remembering these digits was tougher, because you had to remember 7, and when you put in the first 2 and the last 2, it tended to bump out the other ones. That's what science tells us. Take a moment to read what neuroscientist Efrat First says.
Yep.
In that second number, trying to store more than 4 or 5 digits, bumped out some of the digits. Usually people can remember the first couple and the last couple, but not the ones in the middle.
Well, you had 6 numbers and then 3 decimal numbers, so you could get 3 chunks out of it, which I tried to do, but then I lost it.
Usually processing will kick them out, because processing means you stop rehearsing the number like you try to remember a phone number. And that's why I put the processing step in. But it did not affect you much for the first number, for that memorized chunk. At least you had a good shot at the first one. My timer's gone off. Working memory can hold and process 3 to 5 data chunks plus all chunks linked in those data chunks. Given that this statement is true, is this statement true? Please take a read. How many of you say yes?
Yes.
Say yes.
Yes.
How many of you say no? So it turns out that chemistry is, to a large extent, less about logic and more about memorization. Here's what the scientists say specifically. And folks, this is one of the more important statements in cognitive science of learning math and chemistry. So take a minute to read this. It's not enough to memorize something a little. You have to know it really well. And this applies to facts and procedures. What other word do we use for procedure in chemistry and in math?
Algorithm.
An algorithm. An algorithm is a mathematical or scientific procedure for solving a problem. Science says that fundamental, often used algorithms and facts have to be very well memorized. So we got to the question which was brought up earlier. Should kids in chemistry memorize those polyatomic ions used frequently? And what science says is the sooner the better, because if you're using problems to try to remember the formula for PO43-, you tend to not pay attention to the concept behind the problem. So what science recommends is when you first get to a topic, if there's any real simple knowledge that kids can memorize using flashcards, have them do it. Because what that will do is begin to construct this conceptual framework over here. And this over here is the goal. Learning phosphate puts the word into their long-term memory. Learning the formula connects the word and the formula in their long-term memory. Learning a problem where it tells people that phosphate is a fertilizer links additional information to the formula and the term. And the more problems you solve, the better, the bigger you grow this big chunk over here, one big conceptual framework. And what this means over here is, if I mention phosphate, if I mention PO43-, if I mention fertilizer, everything linked to those terms within that chunk springs to mind out of long-term memory for use to solve the problem. And that's what we want, is well-developed conceptual frameworks. But you have to start by memorizing simple definitions. If you let them use problems to do that, learning takes a lot longer. And our goal is to make learning AP chemistry and regular chemistry and college chemistry faster, so we got a little time to do some math.
May I ask a question, Rick?
Yes.
I've always been averse to the idea of flashcards just because they don't work for my learning style. So why not give them a series of worksheets, which they do, 5, 6 different worksheets, which contain, say, 7 essential polyatomic ions, and have them learning through repetitive use as opposed to sitting down with flashcards? Or is it all the same?
Well, cognitive science says, and I'll show you the slide on that in just a minute. Flashcards are the most effective means for learning verbal recall. Because you do rehearsal, and then you do retrieval of phosphate equals PO43-. Now, they also have to practice writing PO43- to remember where the 4 goes, and that the 3 goes on top and in front of the negative sign. So you have to do both, but they're both examples of what we call retrieval practice. And retrieval practice is the fastest way to memorize something. And folks, what the cognitive scientists tell us is, well, take a look at what Willingham is saying here. Take a moment to read this great quote.
Mhm.
2004, I read this and it changed my life. Because I had been telling people, representing them from my teachers union, what the math teachers told me was that, Rick, these calculators are killing us in math. I go to the school board and say, we got to stop calculator use in elementary schools. And they say, why? They'll always have a calculator. What Willingham is saying here is, if kids can't recall the mental math, it takes up space in working memory, and they can't get past that bottleneck. So the fundamentals, whether it's mental math or ion formulas or PIV-NERT or the units we use to measure gas pressure, have to be memorized before they can move on to build a conceptual framework.
Rick, there's an interesting question that I think goes along with that in the chat from Sue Clemmer, who asks, does cognitive science give us any clues as to why students' ability to memorize has degraded so much, especially during COVID? Is it simply the lack of time and engagement in the practice of memorization while we were all doing remote short classes that were asynchronous? And so we weren't doing retrieval practice with the students?
It's a complex problem. Part of it is the inability to give quizzes that count. What do you do when they need to take a quiz and you can't guarantee test security? You can't do a memorization quiz if it's open notes. So I think there was a lot of stuff that happened during COVID we hope to get past and will never happen again. It's hard to say exactly what went wrong. But they didn't lose the ability to memorize during COVID. We might have lost the ability to test them on it. Mary, you had a question.
Oh.
Mary Madden.
Am
I
I
can
on?
see you.
Can you hear me?
Yes.
Oh, okay. I was just going to write it in the chat. In addition, in addition to writing the numbers or the symbols or the formulas or the ions, it's all, and I started this back in college. I know I started this when I student taught, to be sure that I was totally prepared, speaking the symbols and the formulas. So saying sulfate, SO4 -2, sulfate, SO4, it's speaking it aloud. I find myself doing that when I'm doing the New York Times crossword puzzles,
Yes.
speaking the clue, not just reading it off the page through my eyes to
And
brain.
Mary,
And it comes out, and answers come out more readily.
the reason is that human children evolved to learn phrases. That's why they can speak grammatically correct English before they ever get to school, is that built into children is an ability to memorize phrases, which is instinctive. And it's really what makes us human. It's what they're really good at. You can teach a child a foreign language by immersion before age 12, and they pick it up. Try that as an adult. Doesn't work. But children are special because they can memorize phrases so well. But even in adulthood, memorizing phrases is still a privileged activity. We're not as good as children, frankly. But if you read the paper, what they call this is the production effect. Production meaning if you have to say it and you have to write it, it tends to drive it into memory. So you're exactly right. And if you read that paper, when you get to production effect, give a cheer, because that's what you observed in your practice. Ooh, what does not work? What does not work is reasoning based on conceptual understanding. I know you've been told that, some of you folks, but the research that looks into this always says, when people seem to solve a problem using conceptual understanding that is any kind of complex, what they're doing is remembering how they solved it in the past. Willingham's phrase is, understanding is remembering in disguise. And that's what the science tells us. You've been told to use inquiry learning. What does science say about POGIL and discovery science and inquiry learning? Take a look at what Stan DeHaan says. And he's the guy who won the equivalent of the Nobel in neuroscience. Neuroscience says that discovery learning doesn't work. However, I'll say this about POGIL. The evidence is that POGIL works if you do it at the end of a unit. If kids have already built a conceptual framework by memorizing the simple stuff and then solving some problems, they've begun to construct a framework. At that point, experiments of any kind can help to construct that framework more. But if you do POGIL the first day when they don't know any definitions or terms, they spend an hour, they have fun, their ability to solve problems, which is what we want them to do, doesn't go up at all. Do POGIL at the end, or do any kind of lab at the end, and it helps to wire that conceptual framework into information that at least a little bit is already there.
May I ask you a question?
Yes. This is
What,
Todd.
how do you feel about the phenomenological approach to science teaching?
Define it.
Where you take some type of discrepant event and you break it down over, you create basically a unit out of it where you then have to find all the relevant science that kind of goes behind that particular phenomenon.
I won't tell you what I believe. I'll tell you what the guy who won the Nobel in neuroscience believes. I'm sorry to say this. We all want learning chemistry to be easy. We all love discovery labs. I did. I mean, they're great. But the research says the kids just don't learn as much as if you have them establish the conceptual framework to some extent first, and then go to that kind of experience you're talking about. Projects are not bad things. If they know a lot about the topic already, it helps them learn more about the topic, but you can't start by asking them to discover what scientists have taken 500 years to learn and expect it to go very quickly. And we found in our project, to get the teaching a little bit of math they needed, we needed to teach chemistry efficiently and effectively. Oh, the flashcard question. Gary, here's your question on flashcards. The two strategies that are most effective are practice testing, which is flashcards, and distributed practice. Is it back there? Let me give you another sign. What does Dehane say about flashcards? Take a look, folks. I don't like flashcards. I got into an organic PhD program by using flashcards. I found they worked, and that's why I did them. My signal? Who is it that you trust that uses flashcards to get through medical school? The people who show up in the white coats. And part of it is because in math and science, the knowledge we're dealing with is very precise. It's not general. And the brain has trouble learning precise stuff as opposed to summarizing sentences to do speech comprehension. Sorry. And now we're going to try something to see if I can do. Oops. I'm going to stop sharing for a minute. I'm going to try to load up my PDF slides. Give me just a second.
Oh, while you're switching over, Rick, do you have there's a question that came up about flashcards. Denise asked, should students make their own flashcards or should they have access to pre-made cards?
I'm going to answer that in 30 seconds, but my answer is going to be it's best if they make their own. Okay? And I'll get to why that's true in a minute. Here's back at our previous slide, verbatim practice. Let me go up here. Now we're working. Flashcards. I've posted a link to a PDF online that has 100 pages of lessons on how to use cognitive science to teach chemistry. And two of those 100 pages involve teaching kids to use flashcards. And they're free to use. It shows you how to make one-sided flashcards and two-sided. It shows you some examples of the initial flashcards you can make. And this is stuff you can use in class or assign it as homework. Another way to use flashcards. Let's say you're about to start ideal gases as a unit. I say, don't lecture. You want to save time, you want to have fun, try this. Here's the homework assignment I recommend you give the first day. Take a look, read the top, please.
Rick, I don't think we can see what you're showing us.
Uh-oh, I'm sorry. I forgot to do the share part on this. Oopsies. No. Okay. These are my Zoom skills coming in. Zoom meeting, screen share. This one, how about now?
Yes.
Read the homework assignment at the top, please. Thank you for letting me know. Huh. I claim all of these things on this page are fundamentals that are simple and students need to know by the end of the ideal gas unit. Science says the best way to handle these is to ask students to flashcard them in the beginning, not just flashcard them, but write out the answers to some of them. So I say on the first day, hand out this assignment. Tell them what your quiz questions are going to be on the assignment. And say, people, in 2 days, you're going to have this quiz. So instead of lecturing the first day, what do? You do a gas law demonstration. And one of my favorites is, of course, the, get this up here, the pressure versus temperature graph to make a plot in class, because they can't graph without help, that extrapolates down to absolute zero. If you can, if there's easy stuff you can give them to memorize out of class, give it to them. Can your 10th graders do that whole page the first day to memorize over a 2-day period? Maybe not. If that's too much for them, break them in two. Do the gas volumes and pressure at the top and the temperature on day 2, but ask them to make the flashcards and learn outside of class. Next question. In Chem 1, how many people assign questions of this level of difficulty? Molecules to grams. People say yes.
Yes.
People say no. All right. I want to take just a few minutes to teach you one algorithm that Dr. Craig used that worked especially well. You'll have a way to solve this problem, but I'd like to ask that you do it my way, just to learn the method, because for Dr. Craig, it works so well, and you can use it for every type of algorithm in, I'll say this, even in college chemistry, you can use this simple algorithm on half the problems that students solve, and you'll get Dr. Craig's results if you use his method. Here's the problem. Here's your assignment. Take a read and follow the directions. The first question when you answer any question is, in a calculation in chemistry, ask, where am I going? What unit am I looking for? If you don't know where you're going, you're not going to get there. So what I ask students to do is to write down on their paper wanted, and in this case, you wrote down this, right? Chemistry and physics always start calculations by saying, what's the wanted unit? Below the wanted unit on your paper, write this, data, and write 2 blanks. And in that blank, I want you to write a number and a unit. And the number and unit you write will be the first number and unit you come to when you read the problem a second time. So under data, what do you write? If there are 3 grams, write that on your paper. Your paper should look like that. Here's another rule. In chemistry and physics problems, half the time, the data comes in equalities, 2 things that are either proportional or equivalent or equal. And you'll represent them with a slash or a per, or by saying they're equal. I'd like you to go back and read this problem again and list the 3 equalities that are in the data. Am I going too fast? Give you a hint, the first equality looks like this. Because the rule is write a slash as an equal sign. In this problem, is 3 drams equal to 10 links? Yes, if you have one, you have the other. Equals is a little fuzzy here, but we can do this and it will help with conversions. What are the other 2 equalities? That's it. Most data comes in equalities. You write per as equals 1. That's a special rule. Put a 1 in front of the unit if it's a per 1. Now, in most problems, if a single unit is wanted, there will be one item of data that is a single unit. In this data, which is the one item that is single unit data? No denominator. Right here. Add that to the data table too, please. Oops. Does your paper look like this? The rule for word problems is get rid of the words. Convert them to wanted and data. And now I'd like you to on your paper write solve, and below solve write the unit you were looking for. This up here. And now we're going to pick a data item to start our conversions by traditional dimensional analysis. Most of you probably don't write the unit you're looking for in front of dimensional analysis. For reasons I'm about to explain, I encourage it heavily. But, oops. In your data table, you had one item of data which was not an equality. And our rule is going to be, if you want a single unit without a denominator, start with the data in your data table, which was not an equality. Start with the single unit data. Now, folks, if this is a conversion factor problem, how are you going to get rid of links? Because links is not the unit you want, and we want to get to the unit we want. So you're going to do this. You're going to make a conversion, right? Do that in your paper. What has to go on the bottom of that conversion?
Links.
One word. Links. You want to put links where you get rid of it. So the automatic is teach your students to write the single unit and then get rid of it without looking back at the data yet. What does that do? That locks into the first conversion, your first conversion factor, one unit where it should be. And from there, everything's going to chain correctly. Because look back at your data. What is the only piece of data in your data table we haven't used so far that includes links? Use that equality to make that conversion on your paper. Please. Got that? Links is going to cancel. Ooh. We want grains. On the top, we've got drams uncanceled. Where do we put drams to get rid of it? Down here. Do that in your paper. I think you can take it from here, can't you? Because now we're doing traditional dimensional analysis. See if you can finish up the problem using the data from your data table. Most of you teach dimensional analysis to solve calculations. The reason I encourage the wanted in data first is because cognitive scientists tell us if we do that, when you go to write your conversions, you won't be stopping in the middle to figure out what the data is. The units cancel. Can you finish this without a calculator? Can you do the math without a calculator? Give it a try. What happens to the 3 terms here? They cancel to give ones. On the bottom, you've got 10 times 5 is how much? 10 times 5?
50,
And on the top, you've got what?
25.
Ooh, make this a 1 and make this a 2 down here where the 50 was. And now we've got a 2 on the bottom and 4.2 on the top. 2 into 4.2 gives what? I can't see half of my page. Why did we run through all this rigmarole? We went through all the rigmarole because I needed to teach how to do this problem without you using an algorithm that you already knew how to do. I had to use phony units that you wouldn't have a way to solve. And your students are the same way. This didn't quite format right. In this problem, you're going to write wanted to start. And after wanted, what are you going to write? Always write first what? Somebody? The unit you were looking for. Yeah. There you go. There's only one item of data. And notice it's a single unit item of data that goes with our single unit wanted. Special rules for chemistry. Whenever you see grams of a formula, always write in your data table the molar mass of that compound. For NaOH, the molar mass is 40 grams per mole. Another special equality to write in your data table. Whenever you see 10 to 2 digits, always write in your data table 1 mole of anything equals what? 6.02 times 10 to the 23rd particles of anything. And that gives you a paper that looks like this. Is that all the conversions you need to solve stoichiometry? No. You're also going to need a balanced equation and the mole to mole ratio between grams you want and grams you are given. So we call that the balance and bridge steps. Wanted, data, balance and bridge. And folks, all of the conversions you need are now in the data so that when you go to change your conversions, you don't have to stop in the middle to look up the molar mass of NaOH or what will we get in the balanced equation about the ratio of the 2 reactants. Or, oh yeah, what was Avogadro's number? Dr. Craig and our group found that by taking the data and organizing it before you started your conversions, students were far more successful at solving complex calculations of any type where you need conversion factors to solve. And here in this link at the Math of Chem, which is on the Google page, Google Docs page, we've got about 50 pages of practice problems where they can learn these special tricks about in your data table, if you see grams of a formula, write the molar mass. If you see 10 to the 20 anything, write Avogadro's number. A few of these tricks, and it makes chemistry a whole lot easier. All of these rules are in that 100 pages at Math of Chem. Resources on the Google Docs page are today's slides, the PDFs I just put out, 100 pages, 5 articles you can read to follow up, books you can read. And the books look like this. My 8 o'clock one. One of the books I had a hand in writing. Do not buy this book new. It has 500 pages of problems and tricks, strategies, we'll call them, like I've talked about today. If you buy it used, I don't get any money, and I don't need the money. They don't sell these books to high schools because it's a workbook. You have to write in it. But you can use it as a source of problems and strategies. And I think you'll find it gives you some good tips. This is a great book over here to start with. And I've run over, it's 8 o'clock and I have had no time for questions. And poor Kristen is sitting there in the chat room, has 100 questions. What should I do, Kristen?
One of the questions that just came up is how is this going to change the AP chemistry exam now that students can use their calculators for the entire exam? That's a change this year that they'll be able to use their calculators for the multiple choice. Honestly, personally, I don't think it's going to change that much because I think it's only going to be a couple of questions, multiple choice questions that will be affected. Sue Biggs, do you agree with me on that?
My answer will be that during the year, if you want kids to know their mental math, to be a STEM major, they've got to practice their mental math at some points. I would say teach half of your chapters with a calculator and half without. And that sounds weird, but I know people who teach college P-Chem without a calculator, and they get students who go out into other majors really prepared because they can't use the calculator if they can't solve the problem with simple numbers. They don't know the operation. They don't know the order they can't remember how to put in the numbers to the calculator. So I would say if the AP test would go back to doing more math and make half of it mental math, kids will be better prepared for the physics they're going to have to take after chemistry if they're going to be a STEM major. If the kid gets a 5 on the AP test, goes to college, takes college physics because they've got a 5. If they haven't practiced solving calculations, I'm afraid after 6 weeks in physics, they're a business major.
Mm-hmm.
That's my impolitic opinion. Okay. Another question. Prepare the kids for STEM, folks. More questions?
I had a question.
Teresa.
I know when I was in organic chemistry, I'm very much like a flashcard person, but I know in organic chemistry with like all the mechanisms to help with synthesis problems, instead of doing flashcards, I would like write it out. So if I got stuck, I could try to reason through patterns. So I wondered, is that kind of going like for students, like start with the flashcards, but then have something like that so they can try to reason through what they've already done? Just because I'm thinking some things I know, like for me, flashcards weren't like the best way for me to build it, but I know I like flashcards for something. So I'm just wondering how to help with the patterns.
You've said something I should have emphasized. The fundamentals are where you have to start. In an organic, I claim the fundamentals are the functional groups of the simple reactions. If you do not use those fundamentals to solve problems, you will not build that conceptual framework. The key is you have to learn the fundamentals first, then go and write out the production effect like you did of the mechanisms and the problems. You have to move beyond memorization, but you have to start there. So the rules are, and somewhere I had that slide, have the kids memorize the stuff they need often. Have them solve a few simple conceptual problems because the concepts are important, but they can't solve with concepts unless it's really simple problems. Then have them do some algorithmic tough problems. And the combination of all three of those will drive the knowledge into memory and build that conceptual framework. Good point. Thank you.
Okay, so I probably had already done the fundamentals without realizing it. So
Memory is an incredible thing. If you've done some flashcards, it's okay if you forget the flashcards for a while, because what scientists tell us is this: forgetting is your friend. Because the second time you learn it, it'll stick better. And the second time you learn it, you'll learn it in a much faster way. So the real goal in these science courses is not to remember stuff forever. It's to be able to go back in a later course and refresh your memory in 5 minutes. Then you've got it when you need it. Don't expect to remember everything automatically. except your times tables. Sorry. Get up on my hobby horse. Mary,
Yes, because I have to leave to take two grandchildren home who
bless you.
who are not allowed to use calculators, and I'm very happy of that with their teachers, and they're young. But Carrie introduced me to your Chem Review when I began my second career, which was community college teaching, with great success. Your Chem Review is just fabulous because it scaffolds the learning, and there's the X factor, which Carrie has in his PhD thesis, that X factor is us, the teachers, the instructors, and insisting on repetition and pattern and doing it. And I would tell my community college students, don't tell me you can't memorize. You come in here singing the lyrics to the latest pop song, the words to your favorite movies. Every single one of us here tonight, I know, as soon as you said, and we looked at it, you said, sodium hydroxide, 40 grams per mole. We all knew that. Why?
Yep.
Because we memorized the formula. We've made a bazillion solutions using NaOH, and that was an automatic thing. So,
And I love NaOH because it means the mental math is easy. Anybody can divide into 40. Okay.
right. So thank you very much. And I'm going to say bye to everybody. This was wonderful. This was really wonderful. Your Chem Review, I had one copy of it in our community college library so students could come use it all the time. And I had my copy and used it amply.
Thank you. I appreciate it.
Before you go, Mary and Eric, how about Alex? Do you have any comments about Alex? Because that really, the idea of keeping the student at the periphery of what they know and the constant repetition going through different things, how Alex's works, right? They got 100,000 algorithms in there. You can do Alex for math, you can do it for chem now, you can do it for physics, you can do it for statistics.
Gary, I'll claim this. You can do chemistry using only three algorithms. One is the conversion factor algorithm I taught today with the extra strategies. The other is a little different algorithm for problems that require formulas like Pivnert. And the third algorithm you have to know is the Rice ICE BCA tables. I think you can solve all questions using those three algorithms and a few simple strategies of, you see the grams of NaOH, write them over mass. You see M, always write M as moles equals 1 liter. That makes it a conversion factor. It's a ratio. But Mary talked about what the teacher has to do. The teacher has to take this, which is zoomed all backwards, which is this thick, and go through it and pull out what information you need to identify for kids the first day of a unit. What are the small factoids that you just have to know, the basics? What needs to be recallable from memory? We have to do that. In the calculations book, we tried to identify the most important parts of each unit and tell the kids memorize them. If we had to do a third edition instead of a second, we'd do even more of that, frankly. The flashcards have turned out to be even more important than we thought over time. But you have to use what you've learned with flashcards to solve problems and to do labs. If you don't use the fundamentals in the lab, they won't be able to recall them in the lab because the context in which they encounter the fundamentals is so important. And that's why POGO can help. Any lab can help. Take the chemistry and do it on a paper context, but then move it to the lab context. That will confuse them, but the lab will help to straighten it out so they can generalize the calculation strategies to a lab setting. Kristen, you're in charge of time.
Okay, I think in the interest of just recognizing everyone's time, I think we should be considering wrapping this up. I'm so grateful to Rick for presenting tonight and getting us thinking about how we can use retrieval practice and, really bringing all of these different ideas into what we're teaching. If you need the link for the PDP form, I can post that again. We have the Google Doc with all the documents, and we can, if you don't have that, we can send that out again. I also want to put in a plug for NEACT. NEACT is a completely volunteer-run organization, and we hope that you will go to neact.org and join if you're not currently a member or if your membership has lapsed. Your membership helps us bring these events to everybody, and we hope that you consider joining and keep coming to NEACT events, and maybe you'd like to present at a future NEACT event. We want the summer PD series. We'll be asking for that. We have our summer conference coming up. We have ongoing PD all year long, and we'd love to hear from all of you about what you're doing with your students and in your classes to help your students learn chemistry.
Thank you for your invitation to me, Kristen, because I had obviously a very good time.
Yeah.
I hope other people did too.
Thank you.
Last word from anyone?
Thank you, Rick.
Oh, I think
Thanks.
you has a,
Yes,
thank you.
did you have a question? All right.
One more question?
I thought I saw a hand up.
Might have been my thumb. Thanks, folks. Read those papers when you get a chance over the summer. I know it's busy during the year. Maybe tomorrow will be another snow day. Good luck.
I don't know if I can take another snow day. They don't move the AP exam just because we had 5 snow days.
Oh.
Oh my gosh, we had one.
Well,
in,
we
like,
had a snow day, and then there was no power in the building, so we've had 2
Oh,
to back. And Monday was a professional development day. So but most we're going to have 2 days of school this week. So getting
Oh,
a little-
darn.
yeah, it's been kind of a crazy week.
But I know what you're saying about that AP. Thank you, folks.
thank you.
Thank you.